Dear students, last time we have seen kinetics of conjugative reactions. Let us see today kinetics of photochemical reactions. Let us see at first what are photochemical reactions, because unless and until we know what are photochemical reactions and how photochemical reactions differ from the thermal reactions, we cannot go forward the kinetics of photochemical reactions. So what are photochemical reactions? We can define a photochemical reaction, how a chemical reaction which takes place on absorption of light, particularly in the UV and visible region of electromagnetic spectrum, is known as a photochemical reaction. So what is a photochemical reaction? A chemical reaction which occurs on absorption of light, that too UV and visible light, is known as a photochemical reaction. I know that last year you have studied what are photochemical reactions, how photochemical reactions occurs, how photochemical reactions are classified into different classes depending upon the quantum yield of the photochemical reactions. So without going into the details of that, let us see here once again few examples of photochemical reactions. Photochemical reactions are of different types, or in other words, any chemical reaction or most of the chemical reactions can be carried out photochemically. That means we can carry out a chemical transformation, a chemical reaction using suitable electromagnetic radiations. Okay, so with this, let us see few examples of photochemical reactions which are important for us. So the best example of photochemical reaction which is important for us is a photochemical combination. Photochemical combination of H2 and Cl2. Okay, so here what happens? H2 gas and Cl2 gas, when a gaseous mixture of hydrogen and chlorine gas is exposed to electromagnetic radiations of wavelength 4000 nanometer, we get HCl gas. So here this reaction exclusively occurs on absorption of electromagnetic radiations falling in the ultraviolet region of electromagnetic spectrum. So with this, let us see one more example of photochemical decomposition reaction. The photochemical decomposition, photochemical decomposition of hydrogen halides. So these photochemical reactions are again important for us. Photochemical decomposition of hydrogen halides. We know hydrogen halides. How hydrogen halides can be prepared using suitable radiations. The combination of hydrogen and halogens is a very good source for preparing various hydrogen halides like hydrogen chloride, hydrogen bromide, hydrogen iodide, hydrogen fluoride, etc. So without going into the details of that, what the photochemical combination of hydrogen and halides, let us see this example of photochemical decomposition of hydrogen halides. So HI, when HI, hydrogen iodide, is exposed to 200 to 282 nanometer radiations. It gives H2 gas and Cl2 gas. So this photochemical decomposition reaction is again one of the most important example of a photochemical reaction. With this, I think I did not go into the details of what few more photochemical reactions, because we are interested only in what the kinetics of photochemical reactions. I know that last year you have studied so many photochemical reactions and their quantum yields. So with this, let us see the kinetics of photochemical reactions. Now, how can we study kinetics of photochemical reaction? Now, when we want to study the kinetics of photochemical reaction, we have to establish, in case of kinetics of photochemical reaction, relationship between the rate of the photochemical reaction and the intensity of the light absorbed. So that is what the most important thing, because the rate of most of the photochemical reactions, or almost all the photochemical reaction, depends upon the intensity of the electromagnetic radiations used for carrying out that particular photochemical reaction. And therefore, whenever we want to determine rate law for any photochemical reaction at that time, we have to establish, we have to derive an expression for rate of that photochemical reaction in such a way that the relation, whatever relation, final relation which we get, involves what the relationship between rate of that chemical reaction and the intensity of the light absorbed. In few cases, the relation between, in some cases we have to establish relation between rate of the photochemical reaction and quantum yield of the photochemical reaction. So with this, I hope you understood what is kinetics of, or what kinetics of photochemical reaction involves. So in short, the kinetics of photochemical reaction involves what the study of relationship between the rate of reaction and the intensity of light radiations absorbed in that particular photochemical reaction. With this, let us see at first kinetics of photochemical combination reaction between hydrogen and fluorine. In our syllabus, we have to study the kinetics of photochemical reactions are of three types, and the first one is kinetics of photochemical reaction between hydrogen and fluorine. Now this photochemical reaction is again a very good example of chain reaction. It involves two chain propagation steps. I know we did not go into the details of what the chain reactions, but unless and until we know certain important aspects regarding chain reaction, we cannot study what the kinetics of photochemical combination between H2 and Cl2 giving HCl. So here in this case, When hydrogen and chlorine gas is exposed to 400 nanometer electromagnetic radiations falling in the UV region of electromagnetic spectrum, hydrogen reacts with chlorine gas and gives hydrogen chloride gas. So this reaction is a photochemical reaction because this reaction exclusively occurs on absorption of UV radiations of 400 nanometer. Now, the mechanism suggested for this reaction, the mechanism suggested for this photochemical reaction involves following reactions. So let us see the various reactions involving the mechanism of this reaction are: number 1, Cl2 plus H nu gives 2Cl, and rate constant of this reaction is K1, and this reaction is known as chain initiation reaction. Chain initiation reaction, and the rate law of this state is R is equal to K1 into I A. Let us suppose this is what the reaction 1 or chain initiation reaction. Okay. Now here, when we look at this, we will see that Cl2 absorbs photon and gives 2 Cl atoms, and these 2 Cl atoms are responsible for the chain reaction taking place between H2 and Cl2 and giving HCl. The second state in this case is Cl plus H2 gives HCl plus H, and this state is known as chain propagation reaction, and rate of this reaction is given by this: R is equal to K2 into Cl, concentration of Cl, into concentration of H2. Okay. Third reaction is H generated in this chain propagation reaction further reacts with Cl2 and gives HCl, H plus Cl2. Of course, rate constant of this reaction is K2. So here rate constant of this reaction is K3. So H plus Cl2 gives HCl plus Cl. Again, this is chain propagation reaction, and rate of this reaction is equal to K3 into concentration of pH into concentration of Cl2. And the fourth step is Cl at the walls of the container. Rate constant of this fourth reaction is K4, and K4 is equal to 1 by 2 Cl2, and this step is known as chain termination state. Okay, chain termination step, and the rate of this reaction is equal to K4 into Cl. Okay, so in this way we have seen the mechanism suggested for the overall reaction taking place between H2 and Cl2 gas giving 2HCl. This is what the overall reaction taking place on absorption of electromagnetic radiations of 400 nanometer, and the mechanism suggested for this overall reaction involves 4 steps. First step is known as chain initiation step. Here Cl2 chlorine in that reaction mixtures absorbs photon and gives 2 Cl atoms, and the rate of this reaction, chain initiation reaction, is given by R is equal to K1 into IA, where IA is known as intensity of the light radiations absorbed. The second important reaction in this particular case is chain propagation reaction, in which chlorine generated in this chain initiation state reacts with H2 and gives HCl and H. So here this H generated in this state, so called as chain propagation step, reacts in Cl2 and gives HCl, and Cl is generated in third step. So third state is also a chain propagation state. So here we will see that these two steps, step 2 and step 3, are mainly responsible for propagation of this chain reaction. So without going into the details of what chain reaction, let us concentrate on how can we derive the rate law for the overall photochemical reaction involving so many steps. This reaction is a complex reaction, involves all these steps 1, 2, 3, 4, and we know the rate law determination for complex reactions is difficult when it involves so many steps. So let us see how can we derive an expression for rate of this reaction involving all these steps. Before deriving an expression for this overall photochemical reaction taking place between H2 and Cl2 and giving HCl on absorption of UV radiations of wavelength 400 nanometer, let us see at first something about one important concept used for deriving rate law of any photochemical reaction involving chain reactions, and that concept used for deriving rate law of any photochemical reaction involving certain chain reactions is known as steady state approximation. Steady state approximation. Now, what is steady state approximation, or in short, SSA? What is steady state approximation, or SSA? So, the chain reaction, we know, in case of chain reaction giving HCl, we have seen the intermediates, whatever intermediates which are formed in those two chain propagation steps, they are very short-lived, exist for a moment and reacts immediately with the reactant and gives the product. So we know whenever we want to determine rate of any reaction, the slowest state reaction is important for us. And in case of what such fast reactions, photochemical reactions are fast, and therefore the photochemical reactions do not involve the slowest state, and therefore this approximation, steady state approximation, is used for determining rate laws of photochemical reactions involving chain reactions. Now, according to steady state approximation, or sometimes it is also known as steady state assumption, for chain reaction involving many intermediates, I, as shown below, R is giving I1, K0, then I1 is giving I2, and rate of this reaction is, rate constant of this reaction is rather K1. The next one is conversion of I2 intermediate to into I3, and the conversion of I3 into I4. Okay, this is I4. In this way, I4 is converted into IN. Okay. IN minus 1. Okay, IN, and at last IN gives what? P, and so KN. So here this is what the chain reaction. Let us suppose this is a chain reaction in which reactant A is converted into P via all these intermediates I1, I2, I3, I4 and I5. So in this case, according to steady state approximation, rate of formation of intermediate 1 is supposed to be equal to rate of formation of intermediate 2 is equal to rate of formation of nth intermediate upon P is equal to 0. Okay, so here in short, the rate of formation of intermediate is 0. So this is what the steady state approximation. So with this, let us see how can we derive an expression for rate law of a photochemical reaction taking place between H2 and Cl2 giving HCl. We have seen this overall reaction involves four steps. What are those 4 steps? We know those 4 steps. So, making use of those 4 steps, we can derive an expression for rate law of HCl formation. With this, I stop here. Next time, we'll see how can we derive an expression for rate law of this overall photochemical reaction involving 4 chain reactions: chain initiation reaction, chain propagation reaction, and chain termination reaction. With this, I stop here. Next time, we'll see derivation of rate law expression for photochemical combination reaction between H2 and Cl2 giving 2HCl. Thank you very much.